Hi everyone, my name is Agustina. I'm a PhD student in Buenos Aires, Argentina. This is my poster. I tried to guide you a little bit through it in this video. So in this work, what we want to do is a proposal for a transmission measurement that uses a specific single photon source as input. So in transmission estimation, what you want to do is to build an estimator that has as little variance as possible. This depends on two things, on the estimator you choose and on the input beam you send to the sample. So here we can find two important limits. The first one is achieved when you use a Fock state as the input. You have zero uncertainty in the number of photons you are sending to the sample, and in the transmission estimator variance you get what's called the quantum limit. On the other side, if you use a coherent state as the input that has a probability distribution for the number of photons that's Poissonian, you get in the transmission estimator what's called the shot noise limit. In this work, what we propose is to use this specific single photon source. It's based on spontaneous parametric down conversion in this nonlinear crystal, and in this reference here you can find a complete study of this source where we computed the probability distribution in the number of photons at the output as a function of the pump power and the loss of the optical components you need to build it up. So we computed the transmission estimators for these three different sources: the coherent state as the shot noise limit, the time multiplexing source we are proposing, and the Fock state as the quantum limit. We did this for two different situations. The first one is using a number resolving detector for the detection of photons that go through the sample. This gives you, as a random variable, the number of detected photons you have. On the other hand, we used a threshold detector that changes your random variable from number of detected photons to detector clicks. So we computed the transmission estimators for these three different sources in these two different situations. We computed the mean and the variance of these estimators for three different input light conditions. We did this taking into account detector efficiencies and also the loss introduced by the utilization of different optical components. So, as a conclusion, what we found was that in the number resolving case, there are some conditions under which the utilization of the time multiplexing source can give you advantage over using the coherent state for the three different input light conditions. And in the threshold case, we found that using the time multiplexing source can give you an advantage over using a coherent state and detecting it with a threshold detector, but it also gives you an advantage over using a coherent state and a number resolving detector too. So this is pretty much it. If you have any questions or anything you want to talk about, please don't hesitate to ask. And thank you very much for the coherent state as the shot noise, and then the input beam you send to